Oh, no. Yeah.
Questions about anything?
No, I know what it is.
I still have some students who are taking makeup exams, so I'll turn back the exams on Wednesday, not today. Sorry about that. So today I want to talk about zeros of analytic functions, and the moral of the story today will be that analytic functions are kind of like polynomials when it comes to zeros. The zeros have a multiplicity, and they have to be isolated, and you can factor them out in a certain sense. So it's very much like polynomials, and the reason we'll be able to see this is because we have power series now, which look kind of like polynomials. They just have an infinite degree, perhaps. So let's suppose I've got an analytic function, which I know if it's analytic near z0, I can expand it in a power series. And let's suppose z0 is a zero of the function. So that means that f of z0 is equal to 0. And that's the a0 in the power series. Okay, so that power series starts with a 0. And maybe there's a few more coefficients that are 0. So we'll let an be the first non-zero coefficient. Coefficient in the power series. So that would mean that by the Taylor's formula, if you look at the Taylor's formula for the coefficients, that would mean the nth derivatives at z0 would be equal to 0 for n equal 1, 2, out to n minus 1. Okay, and let's see, so now what can I do? Now I can write my power series. It starts with the an, oh, by the way, I should say note. If all the coefficients are 0, then of course the power series is a 0 power series, and then we would see that f is identically 0 inside the radius of convergence. Of the power series. So that's kind of a dumb case. So, but if I have a non-zero coefficient, now I can do this. F of z is equal to, that power series starts with an. So the next term would be an plus 1, z minus z0 to the n plus 1, plus etc. Now you realize I can factor out z minus z0 to the nth power from that power series. So this would be equal to z minus, and by the way, that's just a complex number. So I'm factoring out a complex number from each term. And so this is a real kind of a nothing fact. I'm factoring out a number from this series. So it would start with an, and then the next term would be an plus 1 times z minus z0. I'll do one more term. An plus 2 times z minus z0 squared plus etc. And now here's the brilliant observation, which is more important than you might imagine. So, that this is a power series. So let's call this, I'm going to call this capital F of z. So I'm thinking out loud here. F of z has a power series expansion. And if you think about that power series expansion, it converges for exactly the same z's that the power series for little f converges. And has power series expansion, and this expansion converges for exactly the same z's same z as the series for little f. Okay, that's surprisingly important because that means that the power series for capital F has the same radius of convergence. Consequently, the radius, I'll call them the radii, of convergence are, for f and little f and big F are the same. For little f and big F, okay, so this is actually an important reasoning. And whenever I ask students why that power series for capital F is just as good as the one for F, they're usually at a loss because I didn't make a big enough deal out of this reasoning here. So I'm going to call this important. And it's one of those things that just absolutely no work. We know power series have a radius of convergence, and the fact that these converge for exactly, all I did was factor out that number. So of course they converge for exactly the same z. Okay, and notice that f at z naught is just an plus 0 plus 0 plus 0. And that's not equal to 0. And the fact that that's not equal to 0 means that the 0 of little f has to be isolated. So this is the 0 of little f at z naught is an isolated 0. Meaning I can put a little disk around it. Meaning that there is a delta bigger than 0 such that z naught is the only 0. Of little f in the disk of radius delta about z naught. Okay, that's what it means to be isolated. It means I can stick a disk around it so it's the only one. Okay, so let's think about, that's like polynomials. Polynomials certainly can't have zeros piling up because you can factor them. Because at 0, it's an, capital An, and an was the first non-zero coefficient.
Right, but have we not factored out z minus z naught to be an?
Yes, I'm looking at f of z. F of z is that stuff there, that power series.
Okay.
And if you look at it, it starts with a constant term an.
Yeah.
So it's z.
I thought that f of z was like the antiderivative.
Oh, sometimes I use not today.
That was a mistake. Yeah.
Yeah, not today. Maybe I should call it h. But yeah, it's not an antiderivative.
Right.
Okay, so that's like polynomials. When you factor a polynomial, you see that the zeros are isolated. They don't pile up anywhere. Let's think about this some more now. Oh, let's see. Why is this the case? The y, since f is analytic, let's see, f equals power series. Implies capital F is analytic. Implies capital F is continuous. We know those facts. Okay, and so let's let epsilon, as we've done this before, let epsilon be equal to the modulus of an divided by 2. Okay, so I've drawn this picture before. Let's see. Here's the origin. No, here's z naught. What am I doing? I'm sorry, I don't want z naught. I want 0. And an is a complex number that's not 0. And so I'm going to take the delta. There exists a delta bigger than 0 such that f of z minus an is less than the epsilon in that picture when z minus z naught is less than delta. Okay, so in the picture, the epsilon there would be half. It would be this distance here. That's half the distance to 0. And so if f of z would be in here somewhere, with an epsilon over 2 of an, that means it's staying the heck away from 0. So you see that when that happens, we see that f of z is nowhere near 0. So that f of z is unequal to 0 in that disk of radius delta about z naught. Okay, and so since f is not equal to 0, we have f of z is equal to z minus z naught to the n times my capital F of z. So this is not 0 on the disk of radius delta about z naught, and this is only 0 at z naught. Only at z naught. And we'll say that f has a 0 of order n, just like a polynomial or multiplicity. So here's the definition. We say f has a 0. Some people say multiplicity. Capital N, or order. Capital N sometimes. And it means that in the power series, exactly, the first non-zero term is a capital N. So it has a 0 of multiplicity n at z naught. Okay, so here's a little lemma we proved here. Lemma. If F is analytic on a disk of radius capital R about Z naught, then either F is let's see, if F, I need an F. If F is analytic, then either F is identically 0 on the disk, that's when all the coefficients are 0, or F has an isolated 0 at Z naught. Of some multiplicity, of finite multiplicity. Proof is done. We did it. It was easy. It's just a matter of writing it out, the power series, and looking at it. Proof. One of those no-work proofs. And now I claim this is going to give us a very famous thing about analytic functions called the identity theorem, which is surprisingly important. Let's suppose F is analytic on a domain, omega. It's got to be a domain, omega. And let's let Z sub F be the zero set of F. Let's let Z sub F equal the set of all zeros. So I'll call that the zero set of F. That's equal to the Z in omega such that F of Z is equal to 0. Well, the fact is, if the zeros pile up someplace in omega, then F has to be identically 0. We kind of know that if it was the center of a disk. And knowing that for the center of a disk means we're going to know it in this more general setting. So, if that set of zeros has a limit point, you might remember from Math 341 that word, a limit point, W naught in omega. So the fact that that limit point is in omega is important. It could have a limit point on the boundary. That would be okay. But if it has a limit point in omega, then F is identically 0. Okay, what does a limit point mean? Let's see. Note, W naught is a limit point of ZF, means there exists a sequence of points, Zn in ZF, in the zero set. All the Z's are not, they're all different than W naught for all n. And the limit of that sequence is W naught. limit as n goes to infinity of those points is the limit point. So that makes sense. So you think that the zeros are piling up at W naught. Think zeros pile up at W naught. Okay? Well, that turns out to be surprisingly easy to demonstrate. Question?
So zeros pile up. I'm just trying to think of that, like, I guess physically. That's just they're becoming closer and closer together.
Yeah, you can find a zero arbitrarily close. So, yeah.
Must be like sine 1 over x.
The zeros of sine 1 over x have a limit point at 0. Yeah, that shows it wiggles like hell, and you get more and more zeros, and you can easily see there's if you take a sequence of zeros, in the real line they're well ordered, so you just take them one by one. They definitely pile up at 0. Kind of like crunch into each other. Oh yeah, so that's a good point. This identity theorem is way false in is way false for real differentiable functions. Let's see, the famous function, let's see, why is it? Let's take h of t to be equal to 0 at t equals 0, and e to the minus 1 over t squared, that's the thing that dies away so fast that it smooths the heck out of everything, no matter how weird it is. And I'm going to multiply that by the weird thing, sine 1 over t, for t unequal to 0. That's a famous example of a C infinity smooth function. So a little work will show that that's C infinity smooth on R. And 0 is a 0, and the zeros pile up there. So the zeros pile up at t equals 0, but h is not identically equal to 0. So that's a fact. Let's see, so let me give you the demonstration of the identity theorem. It's basically a picture proof. So the proof of the identity theorem in the complex case. So let's see. Let's suppose W naught is a limit point of the zero set of an analytic function in omega. Okay. Here's my omega. My omega could have holes. Here's my W naught. Okay, my lemma now it's an open set, so I can stick in a disk around here. So omega is open. So there exists a disk of some radius about W naught contained in omega. And now the fact that the zeros pile up there, my lemma implies that my f would have to be identically 0 on that disk. Because the power series would have to be the zero power series. Okay. So here I've got an analytic function that vanishes on this disk. That's going to mean it has to be zero on the whole region. And so here's how you would go about showing that. Being scientific rather than waving your hands about it. Omega's connected. So that means if I pick a z here, pick any old z. So let's pick any z in omega. Well, then being path connected means I can find a curve that starts at W naught and goes to z. Let's call that gamma. Okay, now think about this spot right here. That spot. Think about that spot. That spot has zeros coming from the green line there that pile up there. That means I can do the same stupid thing at that center point and get another disk where it's zero. And I could just keep doing that. I could walk all the way to the end of that curve. That's the feeling. But of course, that's not a proof to think it. Maybe those disks would have to get smaller and smaller, and I'd get stuck and couldn't go any farther. So that's when you try to make a rigorous argument out of that. That's the hang-up. But it's not much of a hang-up because you can get over that hang-up by doing this. It's the classic argument about connectivity. So let's parameterize gamma by z of t as t ranges from A to B. Okay. And so I know that thing's going to be identically zero for a while when I start out at W naught. So the clever thing to do is I like to call it T max, kind of. I'll call it tau m for tau max. I'll call it tau max. Equal the supremum of the tau such that f of z of t is equal to 0 for a less than or equal to t less than tau. So in other words, it's identically 0. Identically 0 until you maybe get to tau, and then that might be the last place. It's hard to figure out how it could be the last place. But let's see, if it were 0 for all those t, then by continuity, it would also be 0 at the end point. So if it's 0 to the left, by continuity, the tau would have to be included in that set. So tau is in the set, in the 0 set. I should say z of tau is in the 0 set by continuity. It's in the 0 set of f by continuity. If it's 0 to the left, then it has to be 0 there too. Okay, I claim that my lemma is going to show me my little lemma will show tau max equals b. So f of z equals 0, 2. And since z was arbitrary, that means that the thing is identically 0. So we conclude that f is identically equal to 0. So having one limit point means we can do this little thing. Okay. Well, let's see, the reason is, let me show you the reason. Let's suppose that this is z of tau max. That means that along this curve, the function is identically 0. So this would be included in the 0 set of f. And so you see that those things pile up. The zeros pile up at z of t max. That means there's a disk that I can stick around there by the lemma where the function's identically 0. So that's a picture proof. So you see from the picture that the zeros, so these are, that purple stuff is in the 0 set. And you see that the zeros pile up at z of t max. Zeros of f pile up along the curve. They pile up along gamma at z of t max. So my lemma means that I can stick a disk around there. There exists a disk, a little one maybe, d delta about zt max, where my f is identically 0. And that means t max is not the max. So the conclusion is T max is not the max. And so that's a contradiction. Let's see, is that a contradiction? It's not the max. That's a contradiction unless we can actually go all the way to the end. So I can, that means that T max is actually B, and I've gone all the way along the curve to Z. Oops, let's see. Lemma will show that T max equals, that's what I'm trying to do, yeah. Yeah, question?
I'm a little confused why, so we defined a disk over W naught, so why could you claim that everything from W naught to the boundary of the disk is in the 0 set?
Let's see. My little lemma, the zeros pile up at W naught. And my little lemma then implies that the function has to be identically 0 on that orange shaded disk. Yeah, if the zeros pile up, then it means that all the coefficients in the power series have to be 0. Otherwise, the 0 would be isolated. Question?
What's the proof that if you have a disk at W naught, that the disk will intersect going along the parameterization? How do you know that the disk will intersect the points forward of W naught? I mean, it's obvious by the picture, but what's the proof of it?
I don't really, let's see, I don't really care about that point. I was saying you can see it, and you would see that, I could make a disk about this spot here if I wanted to. And I didn't want to make an argument of that, because it's exactly because you have to think about stuff you don't want to think about. So that's kind of irrelevant. That was my motivation for thinking, oh, I can extend it a little bit further. But if it doesn't leave the disk, of course there wouldn't be one. But if it does leave the disk, well, what would you take? The first one where it leaves. This is the min of all the, or the inf of all the t where it. So you can do a similar thing. Other questions? That's kind of a nifty argument. Very little work, mostly pictures. And that simple lemma is all it takes. So this is kind of an exciting moment because it means, here's a fun consequence. There's only one way to extend famous functions. Only one way to extend e to the x or sine x or cosine x, the real versions, the power series things you learn in freshman calculus. So there's only one way to extend the real exponential from r to c as an analytic function. I'll call this fun consequences. The y is if E1 of z and E2 of z both extend the exponential, then of course E1 of z, E1 minus E2 is an entire function that vanishes along the real line. And every point of R is a limit point of R. Because the rational numbers are dense. So every point can be approximated by rational numbers. Every point in R is a limit point of R in omega, which is the whole complex plane. So the identity theorem would imply that it's identically zero. So maybe that's overkill. E1 minus E2 is identically zero on C. So check. E1 is the same as E2. Okay, same thing for any other function. In fact, any trig identity any trig identity holds for complex angles. For example, let's think of one. How about sine of alpha plus beta equals, I should know this one, cosine alpha cosine beta plus sine alpha sine, is that it? No, cosine beta. I'm multiplying e to the I alpha times e to the beta, I beta in my head. Sine alpha cosine beta. Okay, so how would I show this? step one, I'd let beta go complex. Step one, let beta go complex. Then I'd have a complex analytic function of the beta equals z, and they would agree on the real line. And so I'd do exactly that same thing. I'd have a complex function on the left, analytic, and one on the right that's analytic. They agree along the real line, so they have to agree on the whole complex plane. So that means I can let the beta go complex. So write beta equals z. We see that it holds for zeta and c. See, it's true for beta equals z on the whole complex plane. Okay, now step two is fix beta again. Fix beta in C. Now do the same thing for alpha. Now let alpha go complex. And you're done. So that's a fun fact. So you can get trig identities for complex numbers without drawing any triangles. Well, let's see. There's one more thing I needed to say about power series. Any questions about anything before I move on? Here's a big fact. Easy big fact. We can differentiate power series term by term. So we can differentiate convergent power series term by term. And the radius of convergence for the derivative is the same. Let's see, so I'll make term by term, which means I'll have f of z being equal to a power series an z minus z naught to the n. And f prime of z would be a different power series. Let's see. When I differentiate it term by term, the a naught would be 0. Let's see, so that's a constant term, plus a1 times z minus z naught, plus etc. The derivative of that a naught term would be 0. The next term would be a1. The next term would be 2a2 times z minus z naught, period, plus 3a3 z minus z naught squared, plus dot, dot, dot. That would be equal to the sum as n goes from 1 to infinity, n times an z minus z naught to the n minus 1. That's what you get if you differentiate term by term. I guess I'm just emphasizing that constant term derivative would be 0. Actually, I could have left, that would be 0 times a0, so that would be still true, even if I started that sum from 0. Let's see, now I can do it, I could change the variables in my, let's see, if I call this n minus 1, I'll call that curly n. Then if little n goes from 1 to infinity, curly n would go from 0 to infinity. And so this would be the sum as curly n starts at 0 and goes to infinity. This would be curly n plus 1 is n. This would be curly n plus 1. And then I'd get z minus z naught, and I like this to be the variable. Okay, but now I haven't quite said the most important thing yet. The most important thing is the radius of convergence of the series for f prime is the same as the radius of convergence for f. Okay, let's see, that's kind of an easy thing to see without doing any work. Let's see, first of all, here's the y. Let's write f prime of z. Well, we know that f prime of z is analytic. F prime of z is analytic where f is. So that means the radius of convergence for f prime is greater than or equal to the radius of convergence for f. Okay, how could it be bigger? And so it can't. So how could the radius of convergence of f prime be greater than Rf? If it were, well, I would know that if it were, the series would converge to an analytic function. Would converge to an analytic function. I'll call it some weird letter. Screwy f. The series would converge to f analytic on the bigger disk and that screwy f would be equal to the f prime on the disk of radius of convergence of little f. Okay. And now we take an antiderivative. Let's let capital F be an antiderivative. This is kind of dope. I'm getting carried away maybe. Let capital F be an antiderivative of screwy f on that bigger disk. Note that little f would be equal to capital F plus some constant because an antiderivative, they'd both be antiderivatives for f prime. And so they would differ by a constant. So note on the disk of radius of convergence of f, because capital F and little f are both antiderivatives of capital F equal F prime there. Anyway, now you see that the power series for little f is the same as the power series for that capital F. Has the same radius of convergence as the series for capital F plus C, and that's bigger. I'm getting carried away with this, which is